Welcome everyone to our third plenary session of the third NOAA AI workshop. And I'm still seeing the number of participants in the waiting room increasing. So I'm gonna give um, 1 more minute to let people join in this session. But today, this session is focusing on trustworthy AI for social goods. And to continue a discussion that we had in the first two plenary sessions about trustworthy AI in the environmental sciences. And I'm Doug Roth, co-chair of the workshop organizing group. And I'm really honored to join by Dr. Ann Bostrom from University of Washington, who is one of the social science experts on our organizing team, where this year we really want to emphasize the importance of social science in the development of AI applications in environmental science. And Anne had a great suggestion of one of our plenary speakers today. So I'm gonna turn the mic to Anne to introduce our first distinguished speaker.
Thank you, Douglas. Did we want to mention the code of conduct too, or is that?
Thanks, Anne. You totally, thanks for reminding of that. I just want to remind everyone of the code of conduct for the workshop, that we really committed to provide the participants of the workshop a safe, productive, inclusive, and welcoming environment for everyone. So we have a full code of conduct sent to all the participants. Please take a look, and if you are experiencing any non-acceptable behavior, please reach out to the workshop organizing group at ai.workshop@noaa.gov. In the meantime, we want to encourage you to submit your questions to our two plenary speakers today at Slido. So you can go to the website slido.com and enter the code NOAA AI 2021. That's the code for the events. And we'll also provide the link in the chat. Thanks, Anne. I think I covered my ground. So go ahead, Anne.
Great. Thank you, Douglas. It's an honor to be able to co-chair this session today. And I'm very honored and pleased to be able to introduce Dr. Emilie Roth to all of you today. Dr. Roth is the owner and principal scientist of Roth Cognitive Engineering, and also, to our good fortune, a distinguished member of the AI2ES External Advisory Board. She's a cognitive psychologist by training, and she has over 30 years of experience in cognitive analysis and design in a variety of domains, including nuclear power plant operations, railroad operations, military command and control, and healthcare. Most recently, she's participated in the design and evaluation of collaborative automated systems for planning and scheduling of air transport missions for the Air Force, which will form the basis of her talk today, Designing Effective Human AI Teaming. Excuse me. Over to you, Emilie.
Great, thank you. And let me switch to the screen and make sure everyone can see it. Can people see the screen? Yes, at this point?
Yes.
Great, okay. So as I mentioned, I'm going to be talking about specific work that I've been doing for the Transcom and the Air Mobility Command, actually over a period of 20 years. But I will frame it in the context of the need for taking what we call a cognitive engineering perspective in trying to think how you join the human and the automated partners, whether it be AI or algorithmic in nature. It's I'm dealing with opaque systems that may not necessarily be that effective in communicating how they come up with their solution. So let's see. First of all, I want to start by saying we're really living in an exciting time. There's great promise and great progress in applying AI techniques to develop very useful and functional new capabilities. So we have more automated vehicles, automated drones, natural language understanding, face recognition, all sorts of decision aids for both military and commercial and consumer applications. And it's really an exciting time. However, some of the basic lessons that we've learned about how to design effective systems and the pitfalls to avoid in some sense, we're finding them that they're getting relearned. So I wanted to just mention a couple of things in that context. I wanted to start by talking about an earlier system, not AI, but just an electronic whiteboard that was developed a couple of years ago. And that's the picture at the top right, I guess, of the screen. So it's an emergency department, and they had regular whiteboards in the emergency department to help them manage their patients and who to see next and where they are. It was decided to develop an electronic version of the whiteboard. And here is a picture early on when they introduced the system. And as you can see, no one is looking at the electronic whiteboard, and everyone is still looking at the hard whiteboard. And the reason for that is, while when they developed the electronic whiteboard, they faithfully modeled the formal elements of the whiteboard, they failed to appreciate all the informal ways that people were using it. And so you can see on the hard copy version of the whiteboard, there are sticky notes, and people use those to communicate collaboratively across positions. They also kept track of their workflow, which patients they'd seen and which they hadn't, and who else had seen those patients. All those were represented in the hard workboard and were important. And unless you really made a deep dive in observing and interviewing and really trying to understand the work deeply, you would miss that. Similarly, more recently, similar lessons have been learned in applying AI systems. And there's a very prominent, well-known recent example that came out of the Google AI labs. And there they were trying to develop a system that would screen patients for the possibility of having diabetic retinopathy, so an eye disease that could lead to blindness. They had the reasonable intuition that if you could use an AI system to do the screening, it would be much more effective than having to wait for people to be screened by human physicians, and especially in poorer and rural areas where physicians aren't regularly available. They tested it in the lab and found that it was as effective as experts in the field. But when they actually put it in the field and tried to observe its use, they found it wasn't effective at all. And the reasons really had a lot to do with the detailed pragmatics of the work environment that simply hadn't been understood and hadn't been taken into account when they were building the system and testing it in the lab. So simple things like lighting quality made it difficult to take good pictures of the patient's eyes. Ditto, just the expertise of the nurses in taking the pictures, and the baud rate of the internet access, which was spotty. All of those things made the system basically have a high false rate, inability to process the images, something like 20%. And as a result, it made the system not useful, because the workflow they recommended is if the system failed to be able to make a diagnosis, the patient was directed to an ophthalmologist. And this was in rural Thailand. It could take hours to get to the ophthalmologist. The people just didn't have the time or the mechanisms to do that. So failing to understand the deep elements of the work really can get in the way of building effective systems. And so the points I want to leave you with, and I will start with, is that in building systems, you really need to understand the broad context of use. Work as practiced is often very different than work as imagined. And if you just sort of take the formal tools or the formal description of tools, you can fail to understand all the workarounds that people do. And successful systems don't try to build automated systems that perform on their own, but try to understand what people can bring to the party and build systems that take advantage of that knowledge. And finally, that it's important to continue to examine and study systems once they're in the field, because just putting the system in can change the nature of the work and it can result in new opportunities for improvement. So those are the big messages that I wanted to start with and that I'll come back to at the end. Okay, so the kind of approach that we take is called cognitive engineering. And the intent of this approach is to sort of say, when you design, you need to think about the capabilities and limitations of the people, the capabilities and limitations of the technology, but also the context of the work. And that's an element that's sometimes missed. Particularly trying to understand the complications that can arise in the work domain that can challenge performance of people and machine agents. I think it's often as useful to reveal the complexities that are going to make it hard for the AI system to perform well as the ones that are going to make it hard for the people to perform well. We try to design for joint performance, and we try to evaluate the joint performance. There are many examples of introducing an automated decision aid into a work environment and actually resulting in poorer performance than if the person worked on their own, because it can sometimes exacerbate their own biases. So these are all kinds of things to think about, and I'll try to talk about some of them. Okay, so I'm going to present a case study of human technology design to spur discussion of the kinds of design questions that designers should ask as they try to build systems. Okay, so the domain I'm going to talk about is military airlift planning. So that's sort of the Air Force's equivalent of FedEx. It's not necessarily attack missions, but more movement missions. So you're moving the president from place to place. You're moving things for humanitarian relief. You're moving things that soldiers might need in operational environment. The taking out of people out of Afghanistan was strongly conducted by this organization. And so what they do is they plan and they schedule, and particularly they replan flight missions to move things from place to place. And this is a typical domain that makes it important to use things like OR techniques and AI techniques to support the scheduling process, because demands exceed resources. There are always more things that need to move than there are planes and then there are pilots to do it, air crews to do it. There are some formal priorities, but often there are also informal priorities, because the formal priorities tend to be very gross. The priorities are fluid. They can change. What requirements are needed can change. What's available, you can lose planes for maintenance reasons. And so everything is changing quickly. And it's a large planning space. So it's really useful to get automated support for this kind of work. And we've built a number of systems. We built, early on, we built systems for dynamic rescheduling during execution. So the plane is already flying, but they have a maintenance problem. How can you deal with it? Initial transport COA development. So you're going into a new place. How should you get there? Should you use a plane? Should you use a ship? Should you move some things by ship to one location and then switch to a plane to be most efficient? Notional asset allocation. Early on, they have some sense of how many requirements for movement are out there. Can they make them all? Can they meet them all? If not, should they shift some in time? And most recently, detailed mission planning. I have a particular thing I need to move. I need to decide what kind of plane, where I'm going to get it from, and where I'm going to stop along the way to refuel or crew rest, things like that. Okay. So what I wanted to do is start by saying to you, the thing I want to leave you with is the kinds of questions that we ask as we go through the design process. So oftentimes when people build new automated systems, the strategy is often try to get the automation to do as much as it possibly can. And whatever it can't do is left over for the human. Or alternatively, sometimes you sort of say, well, what is the human good at and what's the automation good at? Let me design for that. And what we focus more on is what is it that the people are likely to know that the automated system is not likely to know, so that we can build tools where they share that knowledge and solve the problem collaboratively. And that's, I guess, what we mean when we say team performance. So we ask, what are the people on the scene likely to know that the automated aid can't know? And when I say the people on the scene, it could be the end user of the tool. They don't necessarily have to be in the field, that the guys, doing the scheduling. What situations are likely to arise that are beyond the capabilities of the automated system? And how do you best draw on the knowledge and capabilities of the people and the automation to develop the best joint performance that could be possible than either working alone? These are the questions that drive our design. So let me start in this domain. What do the people in the scene know that it's not possible to provide in a formal way to the automated system? The things that come up in real time. So these include dynamics, changes, and situation-specific information. So there's lots of information that's communicated at the last minute verbally. The plane has a broken part and it won't be available for another 2 days. Things like negotiated overrides from standard planning factories. Normally, there are a number of constraints in this domain. So one of them being how many slots there are at an airfield for planes to land and park. That's called maximum on the ground. And usually those numbers are fixed, but there's some wiggle room. So you can negotiate and say, yeah, normally there are 4, but I'm desperate. Can you give me a 5th? And often that can be negotiated. So that's another thing. Preferences. You could sort of say, we're going to have them crew rest at this location because it's halfway between where we're going to need to be or something like that. But some locations have better facilities for the pilots, and the planners have those kinds of preferences, and they'd like to communicate them to the automation. Temporal situation overrides. This airfield is closed for the next 5 hours. And informal changing priorities. I touched on that. If you can't get everything moved, they get on the phone and they negotiate with the customers. You can't move your water supply and your helicopters. Which ones are more important to you right now? And those kinds of changing priorities aren't fixed and can't be communicated in a fixed way to the automation. So in order to optimize joint performance in our world, we answer the question, who does what, by asking who knows what, as much as by asking who is better at what. I'm going to show you an example, but I want to start by explaining to you how it works. The way this works is the user defines the problem to be solved, including adding specific additional constraints that are specific to the situation. The automation generates multiple solutions to give them a choice to start with. The user evaluates and refines the solution, including iterating on the solution, sort of saying, yeah, this is good, but can you stop here instead of stopping there? What would be the effect? And they can refine the solution either manually or through rerunning the system with new constraints. So in this way, the user participates actively in every aspect of the problem. And so the user and the technology form a tightly coupled collaborative team. Okay, the other thing that we do is once you have these idea of what's the user going to do and what's the automation going to do, what's the human bringing to the party, we also have to think about what visualizations do we need to help the user understand the problem and constraints in place and the reasons for the automation to come up with the solution. And those are called observability, common ground, shared understanding of the problem space between the human and the automation, and mechanisms that allow the user to contribute to the common ground, to sort of say, hey, I know you don't know this, but you can't land at this airfield between 2 and 12. And we call those directability, levers for directing the automation. And as I mentioned, also mechanisms to allow the user to broadly search the space of possible solutions. So now I'm going to give you specific concrete visualizations of what I mean. And this is an illustrative scenario from the system that we built for scheduling particular missions. So here is a case where there's some material that needs to go from the United States, from Accord to Balad in Iraq. This was an older example. And so the user simply starts by entering the fixed requirement of the problem. They can add constraints, but in this case, I'm not going to do so. Just the base requirements. I've got to move X number of tons of materials from McCord to Balad. The system cranks out a scheduling solution and presents it in the context of the various constraints that it needed to consider to come up with the solution. This is sort of a kind of explanation. So in this case, it comes up with an itinerary, and it added some stops in order for the crews to rest along the way in Germany and in Anchorage, Alaska, I think. It shows the timeline, of how the flight is going to go, including where and when they were going to rest. And it shows the timeline in the context of the constraints. So I don't know that you could entirely see them, but for every location, you can sort of explore, well, what's the MOG at this location when I land? What's the maximum on the ground? Will I be okay? What's the crew's rest requirements? How long will they have flown before they arrive at the rest location? This allows them to get a sense of how robust the solution is. And again, they can iterate if they don't like the solution. So, but what I'm trying to show here is we try to foster common ground by showing the solution in the context of the constraints. Okay. The other thing I wanted to mention is we provide many mechanisms for the user to add additional constraints to the problem, as I mentioned, because they know things that the automation may not know. So in this example, in Iraq at that time, you couldn't come into the country without first stopping for customs inspection. And so they had to stop in Baghdad. So the human user sort of said, let's take your schedule, but before you go to Balad, you're going to need to stop in Baghdad. And after you return from Balad, you're going to need to stop in Baghdad. They also hadn't liked the fact that the system had been planning to stop in, let's see, I think in Spindaglen on the way back. I think so. So they sort of said, because oftentimes it's a very busy airfield and you could be trapped by MOG. So the user said, don't stop there. Don't stop in this location. There are many mechanisms, as I mentioned, for the users to control the solution. They can say where to stop. They can say where not to stop. They can say, you can stop here if you want, but you can't crew rest there. You can stop here if you want, but you can't refuel. They can place temporal constraints on when they can stop, and they can add stops. Okay, finally, the system tries to come up with multiple distinct solutions, and we actually have mechanisms that allow the user to say, well, give me solutions that involve traversing just different parts of the world, or in this case, using crews that are small crews called basic crews, or larger crews that allow you to fly longer before crew rest. And so we work really hard to come up with operationally distinct solutions that the user can choose among. In this case, there were two solutions given, one for basic crew and one for an augmented crew. The basic crew solution takes longer, it's over a longer span of time, and it has more stops, but it would be cheaper and better to use if you're short on pilots, on crews. The second solution is shorter, but requires more people to fly it. And so again, the human can come in and say, in this situation, we really are going to need crews back by time X. So I'd rather go put more people on so that I can get them back sooner, versus with shorter crews, each crew needs to be only a basic crew. Okay, so I think those were the main points I wanted to illustrate. And so now I'm really just going to summarize them for you. The first point is in driving design, you want to think about what people are likely to know that the automated aid in its regular state can't directly know. And so how do you provide mechanisms for people to provide that? And again, when I say people on the scene, I don't literally mean, you know, people on the ground on the airfield. It could be the planner who's in the process of coming up with a plan, who interacts by phone with the users. How best to draw on the knowledge and capabilities of human and automation to generate a better joint performance. And I hope I showed you that it was very intimate, very tight collaboration between the person and the automated aid. And what visualizations and user interaction mechanisms do you need to foster common ground, a common understanding of what needs to be solved and what are the constraints, and more resilient performance in the face of complexity, unanticipated situations. I haven't talked very much about that, but often that's the real issue. It's not the routine cases where you need more people involvement. It's the cases that are exceptional, where it's important to provide mechanisms to allow people to have more control. Finally, moving back to the very start, in order to make that kind of tight coupling happen and to deal with the complexities, the real complexities in the world, you really need to dig into the context of the work. And that's through field observations, ethnographic observations, focused interviews, there are critical incident interviews. There are lots of mechanisms for doing that, but it's important to do that. When you're designing, you want to think about designing to optimize the joint performance, not just the performance of the automated system working on its own. And similarly, and at least as importantly, when you evaluate systems, you want to evaluate the joint performance and not the system working on its own. And I think that was one of the big lessons learned from the Google example, that just evaluating performance of the automation didn't really wasn't terribly informative when you got it to the field. Okay, so I'm going to end there and give a couple of pitches to some things that are coming up. One thing for everyone to be aware of is the Committee on Human System Integration at the National Academy of Sciences is in the process of writing a report really summarizing the knowledge and research questions associated with human AI teaming. And the report is literally in preparation right now, should be available possibly in the January timeframe, something like that. So keep an eye out for that. And I also have a couple of papers that describe the systems that I talked about and the process that we used. And so I will end there and thank everyone for listening. I'll stop sharing.
Thanks, Emilie. That's a fascinating talk. And
Thank you, Emilie.
Yeah. And I think I've heard the human in the loop in different occasions in this workshop just after 1 day or 1 day and a half events. So we really wish to continue this conversation with you in the discussion later on. So just a reminder for everyone to submit your questions to Emilie in the Slido link that Chris sent in the chat. And it's my pleasure to introduce Dr. Pedro Rodriguez, who is the group supervisor and the senior machine learning researcher of humanitarian assistance for disaster relief and a program at Johns Hopkins University Applied Physics Laboratory. Heather, or I forgot how to pronounce this like acronym, but it is a machine learning and artificial intelligence enabled program to collect and process overhead imagery into categories for analysis. in partnership with the Department of Defense Joint Artificial Intelligence Center, headed ACE FEMA's recovery effort after hazards, including Hurricane Florence, Dorian, and Laura. Pedro also leads various DoD projects, bringing image processing and target recognition algorithms to the tactical edge. And I believe this topic would be really timely, as today we have another landing of tropical storm of Nicholas in Texas. So please welcome Dr. Rodriguez on presenting operationalizing AI for disaster response. Are you muted?
Oh, thank you so much. Can you guys hear me?
Yes, perfect.
Oh, thank you so much for the introduction, and I'm very proud to be here. That was an excellent presentation from Emilie. I actually think there's a lot of connections between our briefings. I'm looking forward to the questions. So, in addition to the introduction, I just want to say that I've been at the Applied Physics Lab for 17 years now. I did my master's and PhD while working full time for APL. So again, thank you for having me here. So I started this briefing thinking that I was going to give a tech talk. So I would say half of the briefing is going to be a lot of pictures, and then the second half I then gravitated back to normal technical slides. So bear with me. Hopefully it's fun. The tech talk slides are fun. So what I wanted to do was I wanted to start with my history, right? So you just heard my technical introduction, but I wanted to give you a little bit of my personal introduction. So, and actually, before being at APL for 17 years, I was raised in a very small town called Guanica in Puerto Rico. It is in the southwest part of Puerto Rico. It has some of the most amazing beaches that I have ever seen. For example, this one in the bottom left is a 3-minute walk from my parents' house. So this is my favorite place to go on vacation. It's inexpensive for me to go, and it's beautiful. And here's a picture with my daughters, my wife, my nephew, and my grandparents who just turned 90 in July. So a little bit of background. And the reason I mentioned that is because, even though it's very lovely to live in Guanica, Puerto Rico, we have to deal with a lot of disasters, right? Hurricanes, right? So constantly, right, through my entire life there, it was every other year we would have a major hurricane come by, we will lose power. And then, as most of you know, 5 years ago, we had Hurricane Maria, probably the most devastating hurricane that has come to Puerto Rico in the last 100 or maybe 200 years. If you Google Hurricane Maria in Puerto Rico, you'll find hundreds and hundreds of pictures of devastation, like this one at the bottom, right? Completely communities flooded. But I wanted to, thankfully my parents were fine, and they lost power for months. Now in Puerto Rico, in many areas, having a solar system. So this is a solar system that my parents installed in their house. It's now a necessity, not just a nice thing to have to power your Tesla for free, right? This is now their daily life. Then, in addition to hurricanes, something that is actually quite new to Puerto Rico is big earthquakes. So we always had minor earthquakes through our history, but in January 7 of 2020, we had a really big 6.4 earthquake a couple of kilometers away from my parents' house. It was very devastating. We had never experienced anything like this. The last time an earthquake this strong happened was literally 100 years ago. And the thing that the history books tell you, they tell you about the foreshocks and the aftershocks. So you always imagine that it's going to be, 5, 10 earthquakes, aftershocks after the big one. What they don't tell you is that it's going to be hundreds of, 3, 4 level earthquakes for an entire year, and they're still going, right? So I think this might have become the norm now for this area of Puerto Rico. So again, this is the elementary school that is the closest to my house, and the earthquake happened like an hour or two before classes started. So you could have imagined how disastrous, how many lives would have been lost if this hurricane has happened, 2 hours later. And then, like everybody else here, we're also dealing with a pandemic, right? So here's the trifecta of disasters happening in this area. While being an island in the Caribbean is not great for getting help for hurricanes and earthquakes, it's actually really good when it comes to a pandemic, right? Because you can control the input of the virus in the airports, right? So Puerto Rico is actually doing really well compared to pretty much every other state in the United States. And in fact, I checked yesterday, and right now they're tied with Vermont in the most vaccinated territory state of the United States. So in that sense, it's very hard. When I go on vacation, it feels great not to have to worry as much about the pandemic. So these are the reason I wanted to start that way is because I've been doing AI and machine learning for 17 years at APL, and I never imagined I would actually start applying my knowledge to disasters that are very close to home. So today I'm going to be talking mostly about the humanitarian assistance and disaster response, which is detecting damage and flooding after hurricanes and tornadoes. There's also work at APL that I'm related to mine about detecting refugee camps after earthquakes or any other major emergency. So I actually found that here there's some tents and some camps that were related to the Puerto Rico earthquake that were found using machine learning and AI. And then finally, the group that I lead at APL is actually in charge of the designing and of the machine learning and data science pipeline for the Johns Hopkins COVID dashboard, which, as you know, is probably one of the first dashboards that went live during the pandemic, and one of the most used by people across the world. And then we also have a team that is supporting FEMA, the White House, many other aspects, many other sponsors on providing analytics on COVID-19. And the reason I like to highlight this tweet is because the cabinet members are holding the PowerPoints that we created for that day, for their daily briefs on COVID-19. So if you have time, 15 minutes, we want to read a very embarrassing history of my work related to humanitarian assistance and disaster relief. This is the link. I'll put it on the chat room later. But again, you can see now that my work has gravitated a lot from my DoD, Navy, etc. kind of work to more working for the disaster response. Okay, so one thing that I wanted to highlight was all those 3 projects are being worked by the same team at APL, right? So very, very diverse topics, right? And very diverse projects, but the reason we have been able to tackle them really fast and stand up pipelines in days and weeks instead of months and years is because we actually have an MLOps team with the one that I lead at APL. So for the people that are not familiar, MLOps is the combination of machine learning and DevOps, but I prefer to describe it this way, which is the intersection of DevOps, data engineering, and machine learning. And it goes beyond algorithm development. So as an example, let me show you this graphic that I stole from the Uber webpage. So they have MLOps teams in Uber. And what they like to highlight is that a lot of people spend time on this cycle. As you can see my cursor, which is the bottom left cycle, which is spending time getting data, training the deep learning algorithms, the NLP algorithms, evaluating them, recall and precision, and then they're done. But the problem is that they're forgetting, similar to what Emilie mentioned, they're forgetting the rest of the process, right? Defining the project. Is the machine learning gonna do really what you wanted it to do? Going back to Emilie's medical example in Google, putting it into production, right? If my network takes, 3 days to give me an answer, is that really useful in a disaster response environment? and truly measuring the impact of your machine learning AI algorithms beyond just the typical precision and recall, right? The measuring the performance of the entire system. So if you're not familiar, any organization out there that is truly wants to operationalize AI, they should have similar MLOps things that we have at APL, right? That take care of not just the cool deep learning algorithm training, but also the data engineering, right? And the DevOps. And DevOps, the old school DevOps is not necessarily applicable to this new machine learning AI paradigm, right? There are new DevOps concepts that need to be developed to handle the unique things about machine learning and AI. So, that was one of the main messages of this talk, right? That all those projects that I mentioned before, they're all leveraging this MLOps best practices, principles, and also platforms that we have developed at APL. So now here's where we stop doing tech talk, and we start having slides with a lot of words, so I apologize. So to give you an example of some of the principles that I mentioned, are very, very typical principles of MLOps are reproducibility or replication, right? Being able to just not only replicate your algorithms, right? Because there's a lot of scientists out there complaining that a lot of these machine learning AI papers that are being published, you cannot replicate them. And that's not really what science should be doing, right? But it's replicating your algorithms and your pipelines, making sure that your pipelines and your algorithms are also reusable. And then finally, make sure that you can manage it, that they have manageability, which is having data governance, model governance, et cetera, and then also making sure that the leaders are getting the value they think they should be getting. So again, this is just very high level. I'm more than happy to provide more details on with the backup slide. But we have a lot of the aspects of our data analytics pipeline for the COVID dashboard is reusing existing pipelines that we had before and expertise and people and personnel that we had before. Okay, so now what I'm gonna do is go deeper on that first humanitarian assistance and disaster relief example that I mentioned that is very dear to my heart. Now the message right now should be operational AI is more than detective scenes with deep learning. So I'm going to be briefing three components of this work: the original header work, which is using machine learning and AI to detect damage and flooding. Something called OX. So here's the Wizard of Oz reference, right? Which is an alerting capability. The tools that we actually provide to the decision makers to truly have mission situational awareness, right? Because bounding boxes on houses and et cetera is not necessarily giving decision makers the situational awareness that they need to make decisions. Okay, so let's go through all of three. I'm gonna go deeper in all three examples. So for the header, again, like I was mentioning in my intro, this was funded by the Joint AI Center. It was one of their first national and missional initiatives. This is a slide that I saw from the Joint AI Center, and it describes the reason why header was a really good project to start applying AI. But in addition to a lot of partners being on class, it does provide a very chaotic environment to apply AI and to see if there's value and impact. And lessons from here at the on-class level in this very chaotic environment can then be applied to our more sensitive DoD projects. So, okay, so one more time, we developed two main algorithms. We had developed more since then, but these are the main. So the first one was being able to take any image from a satellite, from any satellite data or airborne data. So yes, the NOAA airborne data that they collect after hurricanes is exquisite, and it's probably the best data that we have seen. And being able to classify every building as no damage, minor, major damage, or destroyed, which is the categories that FEMA uses. And then we also added classifying if a building is flooded. This is important because here, for example, you can see that the roof is perfectly fine and the building seems fine, but the entire area is flooded. So we had to make the assumption that there is a lot of damage in that building. if the building has a tower or if trees have fallen on top of the building, backgrounds, and things that we don't know how to classify. And then we also have a segmenter to identify water in different areas in the satellite and airborne images. Okay, so I wanted to show, when you're dealing with disaster response, right? It's very difficult to obtain ground truth data to see how well your algorithms are doing. There's other if you're finding cats and dogs in the internet, super easy, right? Billions of images that a human can label. But for damage assessment, not so much. So we actually did a case study for a tornado in Joplin in 2011, where we actually were able to obtain ground truth data. There was ground truth data from people walking around in the ground and assessing buildings. So for example, in 48 hours, this person was able to assess 17 buildings. We also have humans looking at airborne data and satellite data and doing the classification themselves manually. So in this case, you can see the path of the tornado in red, right, and the surrounding areas, and using the 4 categories from FEMA, and they were able to label 6,000 something buildings and houses in more than 168 hours. But what should not be news to any AI person in this audience is, with AI we were able to do in less than 2 hours a significantly higher number of buildings and houses, right? So you can see this. You can see the path of the tornado here, but you can see we were able to do the entire, in this case, image segment, and in addition, add more fine-grained categories than the FEMA categories. What I'm not showing here is just confusion matrices, accuracy, but our results were 90% similar, 90% accurate compared to the human label results, which is the best ground truth that we had. Okay, so we have Hader, which is the algorithm that I described. They're doing really well. Now let's talk about Ox. So Ox represents a very simple tool to provide risk calculation for critical infrastructure. It was based on our work with CISA. What it does is combine the machine learning results and calculate a risk for the asset itself, right, for the critical infrastructure itself, either a single building or multiple buildings, and also calculates a vicinity risk, right? Because again, the machine learning algorithm is not perfect, so it may have actually made a mistake in the critical infrastructure that you were labeling, trying to classify, but that mistake can be fixed if you start looking at the surroundings, right? If every single building surrounding your critical infrastructure was destroyed, there is a chance that at a minimum the building, the critical infrastructure that you're looking at has minimum damage. So there's many ways to do risk analysis, right? This is just an example. Then now what we do is we take that information and we put it into our mission situational awareness tool. So I wish I had more time to describe Dagger. Dagger is a tool that was developed at APL more than 10 years ago, and it was being used for cyber missions, for space missions, and everything in between. What it does is it takes a mission and decomposes in its dependencies, right? So an example that I'm showing here is based on cyber, where you can take a cyber network mission, which is to, in my case, defend the APL network, and I can decompose it from all the way down into the servers, in power, electricity, computers, software, etc. And I can do the same for a disaster response, right? So I could care about my air missions, right? I could care about rescuing people. I could care about providing healthcare to the people in a disaster area. And you can decompose that into the hospitals, into the power generators, into our roads available to be roads and bridges available and not flooded, so you can reach the hospitals, right? So again, I can spend a lot of time. More than happy to answer questions if somebody about Dagger, if somebody contacts me by email. But but what it does is we can now actually provide this information that I just showed you in a way that that a decision maker can actually make decisions. So you can actually identify, oh, I need to put my resources in clearing out this bridge because this bridge is single-handedly preventing me from taking patients to these 3 hospitals, right? Instead of if you just use deep learning and machine learning, right? You're only getting there's 10 bridges that are blocked or flooded or destroyed, but then which one do you apply your resources first, right? So I have a demo of a video since this is an on-class briefing and a public briefing, I created a toy example demo of a scenario during Hurricane Florence. I have a video that I'm gonna go into it and I'll show you the details, but I wanted to, before I change from PowerPoint to video, let me just finish to the slides and then I'll promise I'll get back to the demo. Okay, so future work that is currently being done, right? So we have the critical infrastructure data that we have is being provided by our sponsors, right? Depending on their needs. But there's also a lot of information out there that is open source that we're now including into our risk analysis, right? One of the problems we use in satellite data or airborne data is that you have to wait for the hurricane to pass, right? But in some cases where there's still cellular access, you are getting some data from social media. So people taking pictures of the flooded streets, or et cetera, et cetera. So you can actually start bringing some of those results into your maps, into your data models to start making some decisions before the hurricanes even or the tornado has gone through. Dynamic retraining. So we want to be able to use a lot of the visualizations that I'm going to show you in the demo to allow the humans to fix the mistakes of the machine learning algorithm in a very natural way using the visualization itself, not just having, PhD Python developers in the background. And then processing to the edge. So we have a lot of experience in the DoD of pushing machine learning AI to UAVs, other unmanned systems that are now being deployed. We have worked with the Jake on a project called Smart Sensor that is putting a lot of intelligence into an MQ-9. But we also are bringing that technology to the disaster response. So we're taking all our, in this case, for example, taking our flooding algorithm and making it work on a low swap device that costs $300 that can be put on a quadcopter, or it can be put in security cameras around cities, etc. Right? So if we find a way to be closer at the edge, we can process and provide situational awareness to the decision makers faster. And then my last slide was everything that I talked to was very dear to my heart and things that I'm directly involved with, but there's a lot of more work at APL that is related to the topic of this workshop. And I just wanted to highlight a couple of them before I go into my demo. We have really cool work combining neural networks with physics models for wildfire burn area forecasting. I'm more than happy to give information later. Tomorrow in the afternoon, there's a talk by Christine Piasco, where she's talking about how she's using deep learning models to do sea ice forecasting. And then this is now where we start to get to areas that are not my expertise, but we have work on improving emission and chemical transport models. So this is this work in particular was taking various data sets and trying to predict to very high resolution emissions created by vehicles in the roads. They actually won the best paper award in the Air Vision workshop at CVPR this year, which is a big deal. And then there's also work on increasing the resolution of those chemical transport models. And this work's actually already being done with NOAA and many other partners, across the United States. So again, just a glimpse of other projects that are not directly involved with, but that are going on in APL, and more than happy to connect you to the right people. So on the last 5 minutes, I'm gonna go back to a quick demo. So let me stop sharing, and then I'm gonna share my video. Sorry, I'm looking for it. Okay, perfect. So this is a video where I'm just gonna go brief to it, but again, this is a toy example that we developed for unclassified public showcases. So here what we're doing is we have a very tool that allows you to assign bounding boxes around your critical infrastructure, how big you want bounding boxes related to your neighbors. Here's a very weighted, simplistic weighted average metric for calculating risk for your critical infrastructure that takes into account the machine learning algorithms outputs that I show you. This can be changed to any risk calculation that the people in the community have found to be more beneficial. And what we have done is in the same tool, again, just to demonstrate what we're doing is, here I'm taking data from Hurricane Florence, and I'm actually, every dot here, green dot, yellow dot, represent different categories of our header algorithm, from minor damage to major damage, etc. And then what you're seeing in the circles are the critical infrastructure that was provided to us related to Hurricane Florence. So the square represents the risk based on the asset itself, and then the circle represents the neighbors that we took into account for calculating our risk. We're also showing the data that was used by the machine learning algorithms. So in this case, the humans can go and verify and see if there's truly flooding, if there are trees in top of buildings, if the houses are destroyed. And we're hoping that this is where the user could also provide feedback that could be used to retrain the machine learning algorithms. And then what we're doing is we're now going to this very toy example of a Dagger model. In real life, they're more complicated than this and have more layers. But what we have is our missions at the top, our base infrastructures, and other buildings of interest. So what we can do is we can run the header algorithms on the Hurricane Florence data set, and we can update the different Dagger indicators in real time, right? So right now this is a human doing it, but usually in a lot of our applications for space, cyber, etc., this is just happening in real time. So in this case, you can see that certain base infrastructure and buildings were now orange based on the risk that we calculated on the results of the machine learning, and you can see that these buildings being orange, which is they mean there are more risk of being damaged. It's affecting our C mission more than the rest, right? So again, in more than happy to show you real Dagger models that we have created for emergency disaster response, including COVID-19, which we recently got an award for one of our COVID-19 Dagger models that we created. So I know that was a lot. I tend to speak very, very fast, and when you have an accent like me, it makes it very difficult. So hopefully some of this was understandable. And I'm more than happy to answer any questions in the next section. And I just posted in the chat the link to the article about my work. So thank you so much for your time.
Thanks, Pedro. That is really fascinating to hear from your personal story all the way leads to the work you have been doing. And I want to give a shout out to Rob Radman, who is a lead for NOAA Center for AI. When he was on parental leave, he discovered this feature article about your work. So that's why we decided to reach out to you and to join our panel discussion. And Emilie, if I can ask you to get on camera, and we can, and I will be moderating this Q&A parts. I know there are a lot of questions direct to one speaker specifically, but I think both of us speakers have a synergy on those questions. So do you want to kick us off, Anne, with one question that you choose to ask to both of them, or maybe one of them as a start?
I'd be happy to. Thank you, Douglas. And also this first question, I think, might actually be something that both speakers could address. Can Can you talk about the experience of designing metrics that can effectively capture both human and AI contributions to joint performance? And then there's a sort of a leading question that follows that. Have you found that these metrics sometimes end up being opaque or uninterpretable?
Okay, I guess I will start. We haven't dealt with opaque metrics. We tended to deal with the kind of metrics that the human schedulers normally use. So things like, how long is it going to take to get there? Is there going to be a delay? How many legs? What's the fuel cost? Those kinds of metrics. So we get the metrics from the user community in our case.
Great. Thank you, Emilie. Is that the same for you, Pedro?
Oh yeah, thank you so much. That's the perfect answer. I would say yes, it's very difficult to design metrics for the whole system. One way that we usually go around that is to, whenever we develop metrics, or our T&E systems are actually living in the systems that we're putting in production and deploying, right? So we make sure that, for example, for autonomous vehicles, it will be, instead of having different metrics at different parts of the pipeline or cycle, right? For the islands, independently from this, we usually take the hardware that we put in our autonomous vehicles, and we run the T&E on the actual hardware, on the actual software, with the same cables connecting everything, right? So we make sure that our T&E systems are applied to the thing that is being deployed and put in production, and not just independently in the different parts of the cycle.
Thank you. It sounds like that would suggest that you really need you either need to use in the field testing to look at your metrics, or have some kind of test lab. Great. Thank you. Douglas.
Yeah, I think the second question also applies to both of them. I think there's like two topics. We did not plan like that way, but it all like fits really well together. So this question was originally directed to Emilie, but I think both of you can respond, which is, what guidance can you provide regarding how specifically developers need to understand the scene and the diverse people on the scene, such as like for humanitarian assistance or weather forecasting? How many and which users should be consulted to figure out that what people will know that the AI can't? And I think we also have extensive discussion on this topic in our session yesterday on Trustworthy AI. So maybe Pedro, Emilie, who want to go first?
I guess I can if you'd like. So it's a hard question. How many is always a hard question. There are a couple of answers to how many, but I think the real answer I want to give is to say, to try to make it as continuous as possible. So as much as we can, we try to do observations in the field before we even start designing our systems. We continue during the design process to go back to show systems and to learn. The world changes. The world doesn't stand still. The world changes. And even after you put the systems in, you get surprised. The world continues to change, and your systems don't quite fit anymore. And so you've got to make more changes. I did want to give a shout out. Looking at Pedro's work made me think about Robin Murphy. I don't know if you guys know Robin Murphy, but she is a robotics specialist, computer scientist, I think at Texas A&M, I'm not certain, but she does robotics, but she is really committed to going into the field, both before, during, and after system development, and had some interesting things to say actually about the using image recognition for the collapsed building in the Florida condos that fell, and looking for victims, and the practical constraints on that.
In addition to what Emilie said, I would add that one of the reasons that we found that we have been successful with MLOps is because it has DevOps inside, right? So is we're putting stuff out there and constantly refreshing, right? Instead of searching for perfection before the analysts look at it. So I don't know, I cannot tell you how many people, but I would say that, have a DevOps principles in mind when you do this. And probably Emilie can agree, but sometimes I feel like in some of these areas, it's easier to take a domain expert and teach them the AI than doing it in reverse, right? Again, that depends on the area. I apologize if that's not true for most of you, but in some of our cases, when you're dealing with submarine data, right, it's usually better to take the people that have spent 10 years with that data and show them this new tool.
Excellent answers. Should we move to the next question then? And I guess we're still stuck on trying to figure out how many people and when the design cycle ends, actually.
Oh,
So, if it does, it's unending. Very complementary perspectives on that. The next question here is really devoted to something that you mentioned, Emilie, but I think this also might be something that you both could address. You provided in your talk mechanisms by which users could constrain solutions. So is this something that all AI developers should consider? And so I know in AI, people talk about physics constraints and they talk about ethical constraints on AI models. For example, do AI models need to include mechanisms for users to add constraints and to be trustworthy?
So why don't I start and say yes? This isn't something I necessarily thought about. So oftentimes, I think that the constraints that I often talk about are real-time constraints. But let me give you some examples. Okay, so I can think of two kinds of examples to give you. One in a military context. The notion of risk and how much risk I'm willing to tolerate may vary with the situation. And so that's something that it's useful to provide levers to sort of say, under these circumstances, I'm willing to take more risk to my own troops in order to protect civilians more, or something like that. So there are issues like that. The other is a funny one, which is there are often so back to ethics. There are often trade-offs with respect to biases. You can't have it all. You can't really simultaneously have misses and false alarms that are equally high. If you have more, if you want fewer misses, you're going to have to tolerate more false alarms, that kind of thing. So that's another area, especially when you think about bias and bias against people, things like that it becomes worth thinking about as levers.
Thank you, Emilie. Pedro, misses and false alarms. I'm sure that's true for building categorization too.
Yeah. This is a great question. There's a lot of work in ethics at APL and around us in the Joint AI Center. I think the ethics have been applied the decision making, after the machine learning does its thing, in my knowledge. But there is a lot of work applying the physics. So we in APL we call them world models. So it's the realization that the real world has lots of physics that cannot be broken, right? The speed of light, right? When you're communicating in your cyber networks, or that a car can go this fast, that you can fly this far with this much gas. So there are work that I'm very aware that are combining what I like to call the data-driven methods, like deep learning, with the model-based physics methods together. So that is, I'm more than happy to provide references if somebody contacts me. But for sure, the physical side, yes. I in my work, I have not done anything with the doing ethics constraints.
And I'm going to try to do something dangerous, which is fusing two questions together. That's like up on the list. And both questions are asking about the integration of domain scientists and data science or like machine learning experts together or developers together. So basically it's trying to ask one question direct to Emilie that can you give a rough estimate of how long it might take to get domain science to work in the domain space, to get familiar and situated, to be able to sufficiently understand the important context to avoid the possible failures. And also maybe the other one is more for Pedro, is like what strategies that you may have to be useful to get AI developers and get more immersed in the operations to avoid the whiteboard example that Emilie gave earlier. I know I hope I did a decent job of fusing these two questions together, but maybe Pedro can start with you first and then go to Emilie next. You're muted.
Oh, sorry, this is a tough question. Emilie, if you can go first, I'm blanking out here.
Sure. I mean, I was going to say the same thing, that this feels like yet another question of saying, how long is it going to take? You know, how much do you have to be in? And that is a tough question. It depends on a lot of, I mean, it depends on a lot of things, depends on the domain. One answer is to say, you know, you go back into the field or you do interviews until the value added starts to decrease. And sometimes people say after you've interviewed 5 people, you're not learning anything new. So one answer is, depends, you know, if it's a less dynamic domain, maybe you don't need to interview as many people. If it's a very dynamic domain, maybe you need to interview a lot of people. So that's one answer. The other answer I wanted to give sort of was related to Pedro's. Do you take domain experts and make them AI experts, or do you take AI experts and make them domain experts? And we try to sort of do neither, although I totally get what you're saying, Pedro. We have found it valuable, and it's not done as often as it should, to really get our software engineers to come with us into the field. They don't all like it, and it doesn't work for everybody. So I have 2 cases. I brought in a young man into the field with me, and he was bored, he yawned, he spent the time writing code as we were interviewing the people. So that didn't work so good. Another different time though, it was a different case. It was a young woman, and we were going to do some observations of exercises, and we both were willing to stay up all night to observe the exercises. And I knew this was a keeper, you know, so it varies quite a bit.
Oh, I don't have anything to add to that. That was perfectly answered. And I agree. I agree with everything that Emilie said. I think in our case, when sometimes we have to get the domain experts to become AI experts, is usually in very classified environments because we don't have that many people. But yes, absolutely agree with Emilie 100%.
Great. Okay. Well, I'm not going to be so bold and try to merge questions. I think this next question is a kind of specific question for Emilie. How do you recommend encouraging users to document those times when they had to work around or augment the automated system output and see value in doing so, so that they are helping developers design and implement improvements based on the unknown workflow elements?
Okay, this is a great question to which I personally don't have a great answer. I mean, we've tried by you know, by sending people questionnaires or added to the tool to have people write responses, but people tend not to have the motivation to spend the time to do that. So I think we personally have found it more successful to schedule interviews and ask them about recent cases and problems they've had. I'm sorry to say that, because more automated ways would be useful, and others may have had better experience with that.
Well, at least validates the interviews we're doing now. So thank you, Emilie.
Thanks. And Pedro and Emilie, I have to say we have to come to a conclusion because we have 1 minute left for the session. So I'm gonna thank you all first. And while I'm sharing my one more slide for the screen. So please, 3 things I want to emphasize. One, join this Slack for discussion. Although this panel has concluded, but this discussion doesn't need to end. So please go to the channel 01 workshop to continue this conversation or just share your feedback about this session. And again, join our virtual coffee hours. And today's theme, which is right after this session, is name your AI and ML epic failures. We all have bad experience or failures in the development process. So please join us in the wonder space and to share your experience and learn from others. And the last thing, but not least, we really want to encourage you to join the virtual poster walks. And I don't really need to advertise for those oral sessions because we have great attendance. We have more than 100 people for almost every session. And we want to encourage everyone to join the virtual poster walks and to in the Kiko chat space. And no password needed, everyone can join. And the next session is 4 p.m. Mountain Time. We have a lot of great works in the poster session where you can spend 45 minutes talking with the presenters. And with that, I want to conclude this session. And thank you again, Pedro and Emilie for presenting your work and the discussion. And thank you, Anne, for joining me co-chair this session.
Thank you all.